Welcome. Today, I'm Ted Key. Today, Roger and I, we're going to be talking to you about uh, some work that we've been doing. Normally, we read papers, and so everything's already named. We had to actually decide what to call things. And so, in a few places, we haven't quite exactly figured out on what the right terminology is. But so now we're calling this work MultiDecode. So I'm going to start with some slides to orient you, and then Roger's going to come on and actually show you some code where he did some toy examples with Llama 3.2, so you can actually see multi-decode inference in action. So what are we talking about? So a little bit of the background here is when we train these autoregressive decoder-only models, it's common practice where we use teacher forcing and you learn in parallel from all token positions. And so there are predictions at every token position. And during training, we use every single one of those predictions and we do back propagation. So if your sequence length is 4,000, you actually have 4,000 predictions and you're aggregating the gradients coming from all 4,000 of those before you do a backward pass typically. So in order to prevent BERT-style inference from happening, a triangular autoregressive mask, I think pretty much everybody here knows, is used to prevent tokens from being able to attend to tokens that are later in the sequence. So that's the one pattern we have. The other pattern we have is that during decoding, the common practice is you do some kind of prefill on the prompt, but then when the model is outputting tokens, the common practice is you decode one token at a time using only the prediction from the last token position, which as an autoregressive model, this makes perfect sense. It's only trained to predict the next token. And there's, speculative decoding and there's multi-token, there's different research that's been done to see if we can predict not just the next token, but 2 tokens out, 3 tokens out, whatever. But it's very logical that we just take this last token position. If you think about it a little bit, and we'll go into more of the background, but this is just the overview, nothing stops us from using the predictions at inference time, at decoding time, for multiple token positions. We even train the model to do it that way. We just haven't been taking advantage of that. The reason why we don't is because we want to ensure that every token attends to a logical subset of the other tokens. And the most logical, simple thing is the last token attends to everything that it saw before it. But what we're going to show here is that if you use proper masking, even if you have other tokens that are in there, you can just hide them using the mask so that a particular token that's not supposed to see them won't see them. And from the myopic view of what it can see from within its mask, it will look just like our normal decoding pattern where the nth token sees n-1 tokens that came before it, and only that, even if physically there's other stuff in there that's just hidden from it. So that's the overview of where we're trying to go. So to set up the background, and I'm going a little bit slow here, let's review what's happening in the attention calculation, okay? The true attention calculation in terms of just doing queries dotted with keys is completely position agnostic, and it happens in parallel across all token positions. If you're familiar with the implementation, you just have this large multi-dimensional tensor that has sequence length as one of its dimensions. It has model dimension as another dimension, right? And then maybe, it has batch, but basically then you dot your queries and your keys together across all token positions in one operation at the, like, say, the PyTorch, or JAX level or whatever. Obviously, the GPU has to break it down into smaller pieces and do what it does. So what we do in order to turn this multi-token parallel mess into a 1D linearly ordered language sequence is we use position embeddings. And so we're going to talk about rope in this presentation and in our slides. There's different things you could do for other position embeddings, but rope is one that is particularly compatible with the work we're going to talk about in MultiDecode because the position embeddings are applied late. The position embeddings are applied right before you dot the Q and the K. And so there's much more opportunity to manipulate those rope embeddings. So we have rope embeddings, and then you just say the 0th token gets a rope embedding 0, which involves rotations, and we're not going to go into all that. And then the next token gets a rope embedding of 1 and a rope embedding 2, and so on and so forth. Okay. But here's the main insight is that I read the writing in the margins paper, and there's this one operation where they're doing RAG, and they're taking little notes on different sections of the retrieved data, and then they actually do an extra inference step and then rewind the KV cache to before they did any of this inference. And so the key insight there is that for me was, I've been thinking of the KV cache as this fixed thing, as if it's like burned in silicon, but it's actually very malleable. So then that got me thinking, what other things do I just assume have to work a certain way, but in fact are malleable? And so given that the attention actually knows nothing, it just treats everything in parallel as a bunch of input data queries and a bunch of input data keys. So what do we have control of? We have control over where each token goes. We have control over the rope embeddings assigned to each token. And we have the control over the mask that says which tokens is each token allowed to attend to. In other words, we basically have total control. So I'm going to assert that while the standard pattern is that the tokens are in sequential order exactly the way you would read them in a book, they don't have to be in sequential order. And the rope positions don't need to match their physical. The first token on the left, the 0th token, does not have to have a rope embedding 0. It could have a rope embedding of 5. The next token doesn't have to have a rope embedding of 1. It could have a rope embedding of 1,000. Okay? The next sub-bullet is that not only do they not have to match the physical location they're in, you could have multiple tokens that all have rope embedding 5. Now, it wouldn't make sense if the 6th token could see multiple tokens with a rope embedding of 5. But if there were different tokens with rope embedding 6, and they each could see exactly 1, 5, 1, 4, 1, 3, 1, 2, 1, 1, 1, 0, to each of them, they're just seeing something that looks perfectly normal. Okay? And so that's the idea that we're going to take this attention calculation, which truly allows you to do whatever you want. But we've been thinking very tunnel visioned about trying to match the way we would write out text sequentially if we were just putting it, in a string, in a 1D array. We just pause briefly here. Any questions so far? Okay. So here I have a diagram. This is all still relatively new, so I haven't necessarily gotten a chance to fully label, so I'll have to explain a little bit what's going on here. But imagine that in our LLM, we give it a short string. It's got these 5 tokens. Calculate 5 minus 3, colon. And then it's supposed to just, start outputting tokens. And so what we're hoping is that the next token prediction for the colon is going to be the digit 2, because 5 minus 3 equals 2. Okay? So this is what it would look like in standard encoding. Okay? So I have my queries here across the bottom. And so you can imagine this just being your input to the model. Okay? So at the 0th position, we've got the word calculate, then the token 5, the hyphen or the minus sign, 3, and colon. So these are the 5. I've drawn a couple extra spaces because I'm going to mess around with things later. But right now, these are unused. Okay, this above here is the mask that we will use if we were doing sort of like the first inference pass on this. And what we would do is we would say that the 0th token can only see itself. The first token can see the first and the zeroth. It can see these two. And so in the rows here, I have the different keys, and it's the exact same tokens, right? This is self-attention. So it has to be calc 5 minus 3 colon. It's the exact same thing as here. I just repeated it so you don't have to like mentally remember what's the second token, what's the third token. You can just literally see them here. They're not actually copied in some two-dimensional way. You just have a weight matrix that calculates queries from your inputs, and you have a weight matrix that calculates your keys from your inputs. But there's many places where we do this square diagram to show what the queries and keys are and how the mask allows them to see each other. Now, the important thing here is the mask, I have blue positions showing ones where things are allowed, and yellow positions showing where there are zeros, where things cannot be seen. Gray just means it doesn't really matter at this point. Okay, we're ignoring it. There are no numbers in here, but I wrote numbers onto this mask so that you could see very clearly that, for example, the third token is allowed to see the 0th, 1st, 2nd, and itself. Okay, the true mask is just ones and zeros, trues and falses, or whatever. Okay, and so in our standard decoding, what we see is that the rope values, which are here in italics, they always match the physical, byte location, so to speak, of these tokens in the physical order. Okay, and as you go further in the sequence, the mask is going to be sort of one taller as you go to the right. And this is intuitive. There's zillions of diagrams that show this triangular mask. It's just known as the autoregressive mask. Sometimes you'll see this diagram where, for example, here I have the beginning of the sequence at the bottom and the later tokens at the top. Sometimes you'll see it a mirror image vertically where all of your ones are here in this corner, and then the triangle is shaped a mirror image vertically, of this one. So then that looks a little bit more like a mathematical lower triangular matrix, but it's still triangle shaped, whichever orientation you draw it. So the next slide, I'm going to show a variation on this. But before we go there, any questions about what we're seeing here in terms of this is our input, calculate 5 minus 3 colon, and we're showing here explicitly what you as a user usually don't see, but explicitly we're showing what are the rope embeddings for each token and what is the mask that's being applied to say which keys is each query allowed to see. All right. Going to move on. So now,
hey, Ted, one quick question. You have key rope and key physical position. Why do you have both?
So again, the query rope for a particular token like 5 is always going to be the same as the key rope for the token 5. It's all right. If one of them is 1, the other one's is going to be 1. But excuse me. But I just wanted to repeat everything on the bottom, on the left, because when I start messing with this, it's going to be a little bit harder for you to mentally keep track of where all the numbers are.
Okay. I'm with you.
But there is no scenario I can think of where the token 5, if it's the first token, isn't the first token, no matter how you think about it, from the perspective of a query or a key. Okay. And the 4th token is always the 4th token, right? But yeah.
Okay.
This is trying to be very verbose because we're about to get gnarly.
Thanks for the warning.
All right. So this is the way we do standard decoding. So the first thing I'm going to do is I'm going to say, what if I just shifted things and added 2 blank spaces of ignore this garbage to the beginning of my token sequence? Okay. So now I've shifted it 2 to the right. And so I have 2 tokens of garbage. And what I'm going to do is, these are the 0th and the 1st physical positions. So you'll see that the 0th and the 1st physical rows on the attention masks are all zeros, which means I never allow any of these tokens, calc 5 minus 3 colon, to attend to these. Because if I did, it would change the calculation. Okay? So since they're all masked out, it actually does not matter what these tokens are. Whether this token was the word pizza or whether this token was the word cowboy, it doesn't matter. It will never contribute to the attention calculation because these masks for the zeroth and the first tokens are all zeros. Okay. So what you see is we now have the same triangle, but all we've done is we've now shifted it up and to the right because of inserting two dummy tokens in front of our string. And you'll notice that in this case, calc is still getting rope embedding 0, 5 is still getting rope embedding 1, just like the previous slide. But the rope embedding no longer matches the physical position. Okay, and so the truth is, I could take this calc 5 minus 3 colon with rope embedding 0 through 4. I could put them anywhere. I could slide them around anywhere, and the calculation is just going to be identical as long as I mask out all other token positions so that the token 3 can always see calc 5 and minus and not see colon. As long as that's true, it really is going to do the exact same mathematical calculation. Any questions, concerns that this is not a valid, that this is not going to give us the exact same calculation for the next token prediction on colon? All right, so now I'm going to get even more complicated. Instead of shifting it by 2, I'm going to permute the tokens calc 5 minus 3 and colon. So going back to our original example here, where they're all the way on the left, I'm going to keep these as the first 5 tokens, but I'm going to permute them. And so if I shuffle them and have this weird order, calc 3 calc minus 5 colon, notice that this is still the 0th token. So if I just go by token order, it's still calc 5 minus 3 colon. Okay? By rope embeddings, calc is still the very beginning, and then 5, and then minus, and then 3, and then colon. And then if you said, well, before, 5 used to only be able to see 2 tokens. It used to be able to see calc, and it used to be able to see itself. Well, now it can still see the 0th token calc, and it can see the first token itself, but where they are physically has been shuffled, so this mask looks different now. Okay, and if you look at every other token, you'll see that calc can only see itself, minus can see whatever. The number of tokens that each of these can see is the same, but physically we've just permuted them. Okay, and so my assertion is that this very bizarre permuted matrix, which by the way is no longer lower triangular, you now have got a couple entries over here that are above the diagonal. Okay? It doesn't make sense if you think autoregressive means you can only see to your left. But if autoregressive means you can only see positions that have a lower rope number, then this thing is perfectly good and in fact still meets the exact criteria that the 0th token only sees itself, the 1th token can only see itself and the one previous, the 2nd token can only see itself and the 2 previous, and so on and so forth. And so this, if you were to throw it into a transformer, and I mean any implementation, I don't mean like a custom transformer, you take transformer block from any repo and you will get the exact same next token predictions from colon that you did in the previous 2 slides. So this one might take a little bit longer to absorb, but any questions about what matters is the rope embeddings, not the physical location. I could take this weird blue pattern and I could shuffle this anywhere within the max sequence length of the attention window and it would just be perfectly fine.
I think but in terms of compute, like this is gonna be way less efficient. Right?
I can't tell if you're asking a question. Your volume's really low, Erd.
Sorry, I'll talk later again. I think I need to fix my mic.
Okay, I can hear you. It's just super, super quiet. Um, okay. And so the one thing I want you to take note of in this, we're not actually going to use permutations in multi-decode, okay? But the purpose of showing you this shuffle is that this demonstrates that your masks do not have to be contiguous. If you look at the mask for the token 5, which is the 1th token, okay? It's not the very first one in the sequence, it's the second one in the sequence. It has 0, 1, 0, 1, 0, 1, 0, 1, and then a bunch of zeros from there on out. Okay. So we've now said that things can get moved around and that masks don't need to be contiguous. This is really the basic axioms that we need to say we now have the freedom to create rope embeddings and masks in whatever way we design. So here's the method, okay? For next token prediction at a particular position to be correct, we need to ensure that every token attends to an appropriate subset. And as I've been saying, the subset of tokens attended to do not need to be physically contiguous. They don't need to be triangular. There's no other limitation other than a token should not attend to a later token, meaning a token that has a higher rope number. Okay? In order to meet this minimal set of conditions, nothing prevents us from having multiple positions where we make next token predictions. Okay? Nothing prevents us from having multiple positions that have rope embedding 5. Okay? So when we do this, this will be an exact decoding method. This is not an approximation. This is the exact identical current. I mean, we all know there's like floating point precision limits and hardware implementation limits on multiplying floating point number. But this is an exact implementation. Okay, multi-decode is fully compatible with KV caching, and what we're going to see is that different completions will share subsets of our KV cache entries, which is highly, highly beneficial because the bottleneck for inference is I/O bandwidth. It's the reason why we have so many KV caching strategies. And so by sharing the KV cache, we are limiting the amount of I/O we need to do in order to calculate our attention. So let me walk you through an example. This is a simplified fictitious example. So let's say you're doing a RAG example and you have a story and we want to ask some reading comprehension questions. So we might have in a typical setup a system prompt. We'd have a chunk of data, which is our retrieved story. And then we have our questions like, who is the main character? Where is the story located? If I just pass this prompt into, Llama today, this will work perfectly fine. And what it'll say is it'll say something like, John is the main character of this story. And then it'll continue generation. And it'll say this story is located in Paris. Okay. The observation that we're trying to make here with MultiDecode is that the red and the blue questions don't depend on each other. They're actually both only dependent on the retrieved story. So the reality is you'll get a slightly different answer if you answer them sequentially than if you answer them in parallel. But the parallel answer should nominally be just as good as the sequential answer because there's nothing about where the story is located that truly should depend on how we answered the question, who is the main character? Okay.
Ted?
Yeah.
Yeah, well, that's actually a good point is that in this particular use case, we're assuming that the questions are independent questions.
Correct.
Yeah.
So I was going to give a counterexample. If the first question was, generate some code to do blah de blah. And the second question is, what is the running time of this code? You cannot do multi-decode with it because the what is the running time depends on the actual code that you generated from the first question. Yep.
Yeah, so that'd be kind of an explicit bleed through of information. I think you could get more obscure bleed through where maybe you ask a clarifying question, one question, then a clarifying question that has some context because of the answer to the first one. More so.
Even just like who is the main character, how old is he or she?
Yeah.
Not clear you should answer those in parallel. Now, there is a way in which you could say, who is the main character? How old is the main character? Theoretically, those could be answered in parallel.
Yeah.
Okay. And they could be answered in a way that you and I might interpret and say, that's not a very good answer because the story was about Al and Bob, and Al is old. And the second question was answering how old is Bob, and the first question is saying Al's the main character, okay? But that's just because fundamentally the model's confused about who the main character is. It's not because the decoding strategy was the root of this. The root of it is that the model wasn't really sure who the main character was.
Mm-hmm.
And so it could have hypothetically had a similar mistake even if you did regular decoding, if the model's just really unsure what's going on. Okay, so I'm going to show in more detail, but the idea is if you do standard decoding and it says, John is the main character, the story is located in Paris, that's like 12 tokens or something, and it's going to take you 12 inference steps. Okay, what we're saying is that you can get both of those answers in approximately 6 inference steps. So this is what we're going to do. We're going to mask things so that, let's say the system prompt and retrieve story is 100 tokens. Who is going to get rope position 101, and where is also going to get rope position 101. And then, so 101, 102, 103, 104, 105, 106, right? 101, 102, 103, 104, 105, 106, okay? So the red and the blue tokens are going to double up on our rope embeddings, but we're going to mask them so that the red tokens can see other red tokens and all of the green shared stuff. And we're going to mask the blue tokens so that they can see all the other blue tokens autoregressively as appropriate, right? None of the red tokens that are physically in front of them and all the green tokens that we want them to see. If we do this and we take an inference step, then basically what's going to happen is it'll look pretty normal for the red tokens the way I've written this, because it's say who's the main character question mark, and it's basically just going to pretend that the blue stuff doesn't exist after. That's pretty normal, okay? But for the blue tokens, they're going to act as if the red tokens don't exist at all. There's physically a hole in there, but this is like, remember my second slide, I took tokens and I just slid them to the right. So this is as if you said, system prompt, retrieve story, where is the story located? And just physically shifted those blue tokens to the right. And then we just have grayed out 6 tokens of garbage in there that the blue tokens don't even know that they exist, don't care, don't know what's in there, aren't worried about it. We now run one inference step, and you guys don't know what the actual answer is supposed to be, but I'm just showing that the first token it chose for the red question is John, and the first token it chose for the blue question is Paris. And so our sequence length is going to be system prompt retrieve story, who is the main character question mark, where is the story located question mark, John, Paris. This is one forward pass, but what we did is we read the next token predictions from this physical token position, and we read the next token predictions from this physical token position, and then we appended it to the end. We always append whatever token you predict, right? And so you can use this with zero temperature sampling, you can use this with top K, you can use whatever sampling procedure you want for the next token. But once you've chosen that token, you just append it to the end. In this case, we're appending 2 tokens instead of 1. So for every inference step, we're going to get a red and a blue new token. And I'll show you on the next slide, but before we actually get there, if you imagine this as we keep repeating this, you're going to see red and blue tokens being interleaved. Okay. Naively, if you just read out the raw sequence, it'll be a little hard to understand because it's going to be two sentences that are sort of interleaved with each other. So I'll show that in a second, but any questions before we go to the next slide?
Okay,
Wonderful.
I have a question. Can you hear me?
Yes, now
Okay,
your
okay.
mic's great.
Oh, okay, so like when you're doing the prompting and like generating the thing, are you keeping like two copies of the system prompt retrieve story for each of like, or like is it just one copy and you're appending and inferencing and like moving it out and then appending the new one and doing the inference?
No. So this is the beauty of it. This is literally one input to the LLM.
Okay, I see,
System prompt, blah, 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 retrieve story, blah, blah, who is the blah, 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 blah. What is going to change is the masking and rope embeddings that we use compared to vanilla decoding. But the raw sort of tokens, it's literally as you see it drawn on the slide.
Okay, so like, yeah. But like my question is like this John plus Paris, like does it get generated in one inference pass or like does it take two inference passes?
So basically we input this above here to the LLM, okay?
Yeah.
And let's say our vocabulary size is 50,000. We're going to read out 50,000 logits on this token position. And based on our sampling procedure, right, top K, zero temperature, whatever, we're going to say, oh, John is the next token predicted for red question mark.
I see. It's really nice. I understand.
And then 50,000 logits for this blue question mark. And we say, oh,
yeah.
It looks like Paris is the top sampled token for this guy.
Yeah, I understand. It's really nice.
Yeah. Okay. So let's keep going.
So Erd, I just wanted to real quickly summarize because I think you've mentioned both of them, but there's really kind of two performance wins. The first one is, as you pointed out, for each one of these parallel decodes, we are only reading in the shared context once. So that the bandwidth load is only one copy of that coming through. And then the second one is that every cycle of the language, every forward pass, you get two tokens out of it.
Okay, so it's like 4 times fast.
Yeah. Well, not 4 times, but
not 4 times,
it's twice.
It's two dimensions of win. Because you don't have the IO, you don't have the IO pressure from doubling the system prompt and story.
Yeah. There's less memory and like faster.
Yeah.
Twice as fast.
Yeah. Yes.
You do have to know up front whether the questions are independent.
This only works for independent questions, so you have to have a use case. We'll show you several use cases where you just know up front based on what you're doing. You're doing a search. You're doing a running in the margins. We'll look at. There are places where you know that basically I've done RAG retrieval and I have a prompt I want to apply to each retrieved document. And so it has to be parallel. And so I'm going to get into it, but basically I'm showing you here single data, multiple prompt. But there's actually single prompt, multiple data and multiple prompt, multiple data that you can also do. We're getting a little ahead of ourselves. But
just
absolutely.
Like a thought. So this kind of like decoding would work like really well with the context-based models because like the context-based model, just looking at the prompt, will know what the whole answer is going to be, right? So even if you have like two dependent questions, they're going to know the answer to both at the same time because they're just looking at the context, right? Not the other thing. So
there's going to be a lot of use cases for this, but like I said, generate a function. What's the running time of that function? You can't parallelize that. Definitely cannot parallelize that. Yeah. Jayanth?
Yeah. So from a compute perspective, are we gaining anything? Because the tokens in the red will attend to all the green tokens, right? And so also the tokens in blue will attend to all the green tokens.
Yeah.
So from a compute perspective, maybe it's the same, but bandwidth, the stuff that you and Roger said, those would be the benefit, right?
Very good question. So at a high level, here's what happens. Okay. Um, when you input this, let's use this top one, this whole business into the LLM, okay, you're actually getting next token predictions for every single token, whether you want them or not. We're just used to only using the last one, but the model is physically creating next token predictions at every position because that's how it was trained. Okay. When the relative context length of the green is large, then the fact that you have red and blue is fairly inconsequential. So RAG is potentially a very good use case because if this is thousands of tokens of RAG content, and your question is tens of tokens. The fact that instead of having 10 tokens for your first question and 10 for your second one, you have 20 questions combined is going to be very irrelevant. When your questions are long and the answers to those questions, the completions, are long, then what happens is by doing multi-decode, you're growing your sequence length faster. So if your prompt was write me a 5,000 token poem, and you asked it to do multi-decode 10 ways, that means that you're asking me to generate 50,000 tokens. It will generate them very fast because it's going to do 10 at a time, every inference pass. But you are going to start to see, and if we get to it today, there will at some point be some I/O cost from the fact that your sequence length is growing 10 times faster than it does with a single prompt. It's almost never going to hurt you, but you can think pathologically if these questions were just, if there was no RAG and the question was just, what's the capital of Paris? What's the capital of, or what, I don't know. Some, you can get to a scenario where you're like, it's not worth it to do this. But there's so little overhead for short questions to do multiple in parallel that you almost never lose doing multi-decode because, again, we didn't change the architecture. The model is outputting next token predictions at every spot, whether you want them or not. They're always there.
I think, Janeth, you're right that the actual computational, the number of flops is going to be identical whether you generate 2 tokens in parallel or 2 tokens sequentially.
Except to the extent that a longer sequence length is slightly more flops than a shorter sequence length. Or a slightly longer sequence length, right? A 1020 sequence length is slightly more flops than a 1010 sequence length.
Right, but you would ask the question sequentially. So
depending on how you did it, if you did 1010 and then you did another 1010, then in fact, you're actually half the flops approximately of doing it sequentially.
Yeah.
Yeah. All right. So I have another slide that just shows this more explicitly. So here is just the initial input with the red and the blue question marks. We get John and Paris, and then now the whatever, I don't know what you want to call it, the cursor position is on John and Paris. So we're going to take next token prediction from John. We're going to take next token prediction from Paris, and we get is for both of them. So our new string is going to be, where is the story located? John, Paris, is. We're going to still apply our masking so that red tokens can only see red, blue tokens can only see blue and green. And I just want to note here, even though both of these is's are the same token, and both of them happen to have the same rope number, okay, you cannot combine these because they have different contexts. This red sees the word John as its immediate predecessor, and it also sees this whole question, who's the main character. And this blue has Paris and where's the story located as its immediately preceding tokens. So when attention goes and pulls things forward into the residual stream, these two is's will not be identical. Now, I believe at the whatever 0th layer of the model, the two is's will be identical. Okay, because at that point, all you have is what is the token embedding and what is the rope embedding. Okay, but once you get past the first layer of the model, these is's will not be identical representations on the residual stream, and so the blue and the red is's must stay separate. Some people are incredibly patient. They wait a surprisingly long amount of time. Okay. So more work for Jerry to edit the YouTube video.
Yep.
All right. So I made the point that these two is's are not the same in all the layers, even though they have the same input token and the same rope embedding. So then we're going to do next token prediction on the red and the blue is, and we're going to get the and where. We do that again. We get main and the, and then we get character and story. And so the way you then have to read this out is you have to say system prompt retrieve story. Who is the main character? John is the main character. And system prompt retrieve story. Where is the story located? Paris is where the story, and we didn't quite finish that sentence yet. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tokens that we've generated 100% accurately, as if you had just asked the red and the blue questions separately after the system prompt and the retrieve story. We have 10 tokens that are exact, correct next token predictions, but it only took us 5 inference steps. And that is the crux of multi-decode. We can do multi-decode any number of ways. You don't have to limit it to 2. We could do 3 parallel decodes. You could ask, who's the main character? Where's the story located? What time period is the story? And those are all parallel questions. If you had 10 parallel questions, you could ask all 10 of them. Okay.
So it would be essentially the same as, let's say somehow magically you knew where the sorry, in your previous slide, where the yellow part ended. So it's almost like if you did the red first, and then you didn't change anything and you wiped out the red, and then you did the blue.
Yeah.
I mean, of course, you can't really wipe it out, but it's almost,
well,
if you
actually, you
imagine it that
can.
way.
You literally can
Okay.
delete it from memory and go back to when you only had the system prompt and the retrieve story. You actually can
Yes.
truncate
True.
the KV cache and then start with
True.
new tokens.
True. So it would be
Yes.
similar to that, the gains in bandwidth and everything, right? Yeah. Okay.
Yes.
Cool. Yeah.
Yes. So I gave you one example here, which has 2 questions. You see this branching off from the green where it branches to blue and red. What are the valid patterns for doing something like this?
Hey, Ted.
Okay. Yeah.
Harold had a question in the chat.
Oh, sorry. Yeah, I've been trouble
No,
monitoring the chat.
I wasn't quite sure. I didn't quite follow.
Let's see if I can. Which question is this?
Harold, are you online? Can you voice? I'm not understanding quite what that question is.
I think it's the last question.
Yeah, Ted said that there's no essentially no predictions. It's exact token output. Can you elaborate on that, please?
I'm saying this is not an approximation of what would have happened if you had asked these 2 questions separately. This is the exact floating point values you would have gotten if you had said, system prompt retrieve story, who's the main character, and just had it do completion. System prompt retrieve story, where is the story located? Question mark, and just have it do completion. You will get the exact same floating point values. This is not a trick that approximates it. This is literally the exact same calculation. So sometimes when you read ML papers, they're saying this is an approximate way that we hope is good enough for us to do completion and still get high accuracy. This multi-decode technique will give you the exact same accuracy. So if the model, when you ask it one question at a time, can solve this math word problem, it can solve the math word problem with multi-decode because it's an exact calculation. There is no degradation in the LLM functioning. Does that answer your question?
Yes, thank you.
Awesome. All right. So I showed this one pattern, and the question is, what are valid patterns? Okay. So the standard decoding pattern is a linear sequence. And what I showed you was we had some amount of shared stuff, and then we branched to the red question and the blue question. And branching is a perfectly valid causal pattern. And you'll notice that if you assume the proper masking, which I haven't shown on here, every token like this blue 4 sees exactly a 3, a 2, a 1, and a 0. It doesn't know anything about where these red tokens live. It doesn't care. Every token sees exactly what it's expecting to see in its ancestry, so to speak. So you can branch more than once. Any tree is a valid pattern. And if you look at all the 4s on here, each 4 can see exactly 1, 3, 1, 2, 1, 1, and 1, 0 in its ancestry. But the reality is you don't have to limit yourself to a single root. Any forest is a valid pattern because these 2s see a 1 and a 0, and these 2s over here see a 1 and a 0, and it doesn't matter the fact that they're not sharing anything. And so this case here was one set of shared data, multiple questions. When you get to a forest, now you're talking about multiple data, and we're not sharing the data. We don't have to share data in order to do multi-decoding. Just checking the chat real quick. Yeah. And so this is right. This is not about optimizing GPU utilization in the sense of like ordering and chunking things. This is saying that you did an inference pass, and if your sequence length was 1020, there are 1020 next token predictions. We've just been ignoring 1019 of them. We've been throwing them away, and there's no need to actually throw them away. So ultimately, if I had something like this forest, I need to pack it into an array. I need to pack it into a single linear sequence. How do I do that? So if I have a tree or forest, again, the requirement is we just have to preserve the causal chain, and it's not 100% required at the very beginning, but that thing I showed you with shuffling the tokens, there's no reason to shuffle the tokens. That's just a nuisance. That just makes it mind-numbingly hard to read the tokens out and see if the mask is accurate. So you can do a depth-first search, okay? And so here I could just say, I'm going to literally place the tokens in my array as green 0, green 1, green 2, red 3, red 4, red 5, blue 3, blue 4, blue 5, yellow, and do a depth first search. Okay, that would be a valid ordering. I could do a breadth first search, and I could do green 0, green 1, green 2, yellow 2, red 3, blue 3, yellow 3, all these. And you'll see that it is always the case that anything that's an ancestor appears to the left in the sequence. And again, all that changes whether you do a depth first or breadth first search is what the mask exactly looks like. Depth first search will tend to give you the nicest, most triangular looking subcomponents of your mask. And then the reality is you could do a mix of depth and breadth first, where I could start by doing depth first search up to here, and then I could decide for no good reason to then alternate and do a breadth first search and do yellow 4, purple 4, yellow 5, purple 5 instead of continuing on to do depth first search. But basically, like there's not a whole lot of restrictions. As long as you just do this, you can pack these forests into our linear array and pass it into our transformer. The hard part really is the bookkeeping. Okay, you got to do some bookkeeping so that you have the right rope numbers and you have the right mix. So let's talk about some use cases. Yeah, I just want to do a quick time check. Okay, so there's more use cases than I can fit on this slide, but a couple of things really jump out. Okay, so if you are trying to do advanced decoding one token at a time, there are already methods right now that consider doing a little bit of a tree search, some calculations, whatever. Right now, doing any of those is expensive because for every node in a tree that you consider, you're doing an inference pass. If you use MultiDecode, then you really only need as many inference passes as the height of your tree. And so it's logarithmic in the number of nodes in your tree. And so you can do beam search or some other search algorithm, and you can search further ahead. There's a paper I have in the references, the look-ahead decoding paper actually does a form of multi-token search, and then like speculative decoding, it does a verification step. But the cool thing is they actually use a form of multi-decoding in order to make this look ahead and verification cheaper. They don't do it just one at a time. But I think I'm guessing the authors failed to see that there is a much more general pattern than just this look ahead decoding, that you can do any kind of multi-decoding and far more flexibly than just this very specific pattern. If we have time, we can talk about today. We'll talk about writing in the margins. And what writing in the margins does, I think I briefly mentioned, it does RAG, and then it asks a question. If you have a user question you're trying to answer, okay, then it applies that user question to each chunk coming back from RAG. And it calls those margin notes, like you would have margin notes on the side of a page of a book or something. And then it does some work to collect those notes together and append them to the end. And then finally ask the user question. So what we're doing is we're asking the same question over and over again about the data coming back from presumably our vector database or whatever. This is a embarrassingly parallel use case where we're asking the same question many times over. If you're doing chain of thought, I don't know exactly what ideas people have, but instead of having sequential chain of thought reasoning, you can actually start saying, well, one thing I could do is A, and another thing I could do is B. Right now, the LLM has to sort of remember A and remember B and explore one of them and just leave the other one sitting in context and then proceed. Hypothetically, you could have the LLM do a chain of thought where it says, well, there's sort of like A and B as my initial things. And then instead of having to continue, you can then copy A and B and do parallel decoding on both A and B ideas simultaneously. And so then it might say, well, I have 3 things I can think about for A and 2 things I can think about for B. And you can do 5-way multi-decode on A1, A2, A3, and B1 and B2 simultaneously. Now, again, the more multi-decoding you do, the faster your sequence length grows. And for some use cases, if these completions are very long, you'll start to see some I/O pressure from the longer context lengths. We showed our example of fast, cheaper answering of multiple independent questions. Right now, you might say, I don't often have that many parallel questions, but if when you went into the ChatGPT UI, right now there's a little box at the bottom, okay? If instead it just had multiple boxes and you could type as many questions as you want, and if you were paying for ChatGPT, instead of paying per token for all the things that you typed, if it said, now, if you type 3 questions in these boxes, you're only going to pay for the longest of those questions. And when it does completions, you're only going to pay for the longest of those completions. So if you get 3 completions that are all approximately 1,000 tokens long, they may say, we're only going to charge you for 1,000 completion tokens instead of for 3,000 completion tokens. Suddenly, if that was the pricing model, you might decide, I have a lot more parallel questions that I can think of that I would just plop in there because questions 2 through N are basically free. And then finally, the last idea is, I don't know how often this would happen, but if you have a multi-user server and you have a long prompt that has, let's say, a 10,000 sequence length, okay, and you have a bunch of users that are asking really short questions like, what is the capital of France? You can pack all of those short questions in the 10,000 space you have in the other batch entries. Okay. And so potentially, let's say you could fit, let's say you're using batch size 8. If you can fit 10 short questions in your 10,000 sequence length, then instead of being able to do with batch size 8, 1 long one and 7 short ones that are wasting all that extra capacity, you can actually fit 70 short questions in a batch size of 8 with the exact same compute. Because right now, when you have a batch size 8, it's doing a bunch of zeros, as far as I know. It's doing predominantly a calculation on the full 10,000 length, even though 7 of them are just filled with, zeros. There may be some optimizations where the CUDA kernels can tell that something's all zeros and it actually skips it. But nominally, at roughly the same cost of doing a batch size 8 with 1 long and 7 short users, you could do 1 long and 70 short users. And so, again, as the OpenAI or whoever, you've now gone from handling 8 users to 71 users, a 9-fold increase in the number of users that you are able to respond to with the exact same compute without getting any degradation in model performance, because this is an exact calculation. All right, I think that's the end of the slides. So I just have a summary here. So we're taking advantage of the parallel aspect. I've said it a million times. Reminder, this is an exact method. It does not require that you have a special model. It doesn't require that you have any special heads. It doesn't require the model be trained any differently. It doesn't require that you have any special hardware. And Roger's going to show that on a Hugging Face Llama right now, he's able to do multi-decode, even though nobody ever thought that to design the software to support this. It doesn't really. Now, I do think that the performance optimizations, the speed of doing multi-decode can be improved with more baked in support. Some of the bookkeeping Roger's doing manually, but with multi-decode built in support, it might be able to be done a little bit more efficiently. So the only thing we require is that your LLM software allow you to specify custom masks and custom rope embeddings.
This is very exciting. I will say the possibility of layering this on top of the like entropy decoding or the sampler stuff, and then also using R1, which right now they updated it yesterday and it's beating Opus and O3.
If you do a tree search for some kind of entropy sampling, you're only going to pay for log n inferences instead of as many nodes as you have inferences.
Oh man.
Yeah. Wow. And here's the crazy thing. Okay. At some point you will Roger, if we get to it, has a chart that shows you actually as your sequence length gets really long, there's some IO pressure and the cost goes up. Okay. But the crazy thing is that until you have that level of IO cost, the branching factor of your tree is free. So whether it's a binary tree or a ternary tree or a 10-way B tree or a 30-way B tree, the cost is roughly dependent on the height of the tree, not the width.
Huh.
So you can do a fairly wide, expensive tree search because all of the nodes at the same height of the tree get done in one inference pass.
Well, I mean, yeah, so tree wise and graph wise, right? I
Yeah.
just linked it in the chat, but there's like there's a whole I don't know. I like graphs. I like knowledge graphs a lot, and if I can just like knowledge graph an entire knowledge graph every time I do an inference pass, that could be
Yeah,
cool.
you do some sort of tree walk of that subset of the
Yeah,
graph, and then yeah.
Yep.
Ted, when you say the expense, are you referring to computationally or storage, both?
Yeah, computationally, the number of inference passes is your largest cost.
Okay.
Okay. Now, again, at some point, as you get extreme, if you said, what if you did 500-way multi-decode? Okay, that's going to bloat your sequence length, and then your cost per inference step is going to go up.
Right.
But if you don't go to that ridiculous extremes, if you just do 3-way, 5-way, 10-way multi-decode, the sequence length isn't that different. And so it's basically the same cost to do inference on one next token as 3 or 5 or 10.
Okay.
You may have like a 3% performance penalty or something really small.
Yeah, but it's just the dollars to compute, it just sounds like it's dramatically lower. So
Yeah, like to get 10 times as fast token prediction at a 3% cost. Like that's just freaking ridiculous.
Yeah, that's like free money, or whatever you want to call
It
it.
is free money. It literally is. Like,
Yes.
there's a
Yeah.
couple of companies, like Prime Intellect comes to mind. There's a lot of people that are doing like full-on distributed training of models, right? Like, but the problem is you can only get to about like 40B because you got a bunch of like the latency and like weird hardware and all that crap. But if you could get it, like if you can do reasoning sort of search is per like during your generation kind of with this technique, like you could just give everybody free AGI forever.
Yeah. So I talked about
Just
like
saying.
ChatGPT possibly having multiple text boxes and saying the cost for additional text boxes is less than the first one.
Centralized network of optimizing those. Yeah.
Another possibility as an LLM vendor is you could say the max sequence length for this LLM is 128,000. But if you go to this drop down and you opt to say this question is not going to require more than 16,000 tokens total, then I know I can pack 8 of you in my 128. And so your token price, if you self-limit to 16,000, your token price will now be, let's say it's not 1/8, it'll be 1/6 of if you ask for the full 128. If you say my token limit is only 4,000, now I can pack whatever the number is, 30 of you in there, whatever. Now I will offer you your inference at 1/20th the cost of full price. To me, it's a no-brainer.
Yeah, you get ChatGPT for like a quarter, like you're good. You got as long as you got, most of your chats, you don't need to persist through too many turns and they start getting stupid anyway. So it's like, you could totally make it.
And the control will be yours if you want to go full cost, just ask for everything.
Right.
But
already how they're doing it with reasoning anyway. Like people are getting used to that.
Now, if you have the most capable reasoning model and it's doing very long chain of thought, so it's doing thousands and thousands of tokens, filling up its context already, you probably can't optimize that because you're already using the full context length.
Sure, yeah.
You can still do what you're talking about, Warren. You can do search on your per token decoding, but you can't really pack multiple users in there because each user is really fully utilizing the whole thing, potentially.
Well, yeah,
I,
I feel like those you want, those cases you just handle with like an ensemble of agents, right? Like you go up a level where you don't have to worry about the
Yeah.
model anymore, and you're just like, hey, do you guys want to like
Yeah.
point your robots at really hard problems? Like now you can have a couple of bucks, which will cover you for the next 3 months of all the chat GPT you want.
Yep. So Roger, do you
Ted,
want to?
yeah, I wanted to clarify one thing on that.
Mhm.
If I have if I don't have anybody else sharing my batch, my mini batch during inference, then a bunch of similar sized short context, well, actually, it doesn't matter what context, a bunch of similar sized queries, independent queries to separate context would be just as efficient by just expanding. I use up the whole mini batch basically,
Ensemble
right?
everything, right?
Yeah,
Yeah.
right.
If they're
So your
similar
idea,
length,
yeah, so the idea of having a bunch of small ones with a big one is because you have a big batch anyhow, and you're adding in a bunch of small ones into it.
yes, that's to me sort of the introductory version. But then my thinking is if you know you have this technique in your tool belt, then you do the thing I talked about where you give users the ability to opt for a shorter max sequence length. And then you can just pack things very efficiently.
Mhm.
Right. So you can have people who opt for 4,000 mixed with people who opt for 16,000 mixed with people who opt for 64,000 because they all have just chosen and you just, block them in.
Yeah, I don't know how in production language models how dynamic that is. Like, do batches get, queries get moved around from one batch to another?
I
Is it
know
kind of
for
a,
I know for most of like I that's for most of the time when you call like the prod APIs, like you set max context like you always tell them this anyway. So there's probably people who are doing something close to this already where they're like, as they come in, you tier the requests based on what the user
Mhm.
is saying the max context is. Um, and usually at least like in some front ends there's even like a slider for it too, so I like normally it's 128 but I'll take it down to like half that if I'm only like just starting out and asking a couple questions kind of thing.
Okay.
Yeah.
Yeah, that's consistent.
And there's definitely a thing you can do where you sort users by their length. So you put all similar short ones together and you put all the long ones together.
I know that's one of the things they do with Claude code where or like the thing here is reasoning tokens, right? You can set if you set your reasoning effort to like maximum or like in Claude code you specifically use the word ultra think. What that does is it changes the maximum amount of tokens that can be spent on reasoning to the maximum that it can be, and just like tells it to keep printing basically. Um,
Yeah.
and
Yeah.
so
So
you
It
that's when
prints
you have
tokens and you print bills to pay your Claude
yeah.
yeah, that's when you have the
invoice.
unlimited credit card or whatever to the
Well,
account.
yeah,
Right?
you give them $200 a month and they'll be happy to do that. But he feels I was just messing with him today. I was trying to get him to set up my weird shell environment, and he just like I don't know what they did. I think they quantized the hell out of him or something. But he feels so stupid now. I don't know what happened, but it was way better like yesterday. But thankfully, DeepSeek, they dropped R1, so we're good now. Like I don't need to. I don't need to pay Dario anymore. I can swap over to paying whoever.
So Roger, I think we might want to allocate some time next week, but do you want to give people a look at some of the coding examples? I think it's fun to see it like not just on a
Yeah.
slide, a
Yeah,
theoretical,
I want
but
to
like
watch it.
this actually ran on Hugging Face.
Yeah, yeah, we can do that. I think we can we're not going to have a lot of time to go through, but
Yeah.
Give us
Or
the
even
10
just
minute
we can at least
version.
one
go
or
there.
two,
So,
The 10-minute version,
yeah.
Raj.
Well, or at least the first 10 minutes of a 50-minute version. How's that?
Okay, that's fair. Well, that is,
Isn't that more
this
realistic?
is our forte of turning
No,
1 week into like 3 or 4, right? So
Yeah.
This is a
So
trailer
I
for the
will.
next couple of months.
Yeah, that's
yeah.
right. So I will go ahead and drop this particular notebook this week then. I'll do it a couple places. I'll do it on the Google Drive and do it in our GitHub repo.
Roger,
well.
before you go too far, do you have any idea on the resources needed? Is this something somebody can run on a local machine, or are we going to have to pony up some cloud money?
It all depends on what language model you want to use. It's kind of arbitrary. I happen to build based it on the Llama, what was it, 3.2, 1B, I think. There is one constraint. Technically, Ted, you can use it for any transformer-based model, but it does have to have this restriction that you have to be able to specify during inference the custom attention mask and the position encoding. I think you did call that out in one of your slides. So I happen to pick, I think the most common ones in Hugging Face support it, but not everyone. I forget which one I was trying. There were some that don't. So it's kind of an opt-in type of thing. So, but it is a standard API for Hugging Face. So to go through real quick, I think I'll just spin through the code quick and then maybe look at the first example at least, the output from it. So standard stuff includes log into the Hugging Face to be able to download the model. This is the main functionality, so the multi-decode generator. It accepts your input IDs, which would be your tokenized context. The RAG or system prompt would go in here. And the questions, I guess, as well. The positions would be when you're specifying the positions for each of the tokens in that input IDs. The mask, we looked at it a couple of ways. We actually, when Ted and I first started looking at this, we were looking at more of a beam model. And so we were it kind of coded the core implementation around implementing a beam search. In here, we decided, for kind of playing around with it, we've got this engine that once you set up your masks, you set up your positions and your input sequence, then it can run and generate text. And that kind of fits all these different use cases. So that's what this attempted to implement, and not really paying attention to efficiency on this implementation, but just flexibility. It's got the core building block that you can feed in. It's a bit of work setting up these things before you can call it. But yeah, that was the concept. Okay, so the inputs, I'll dock this a little bit better before I post it. But again, the input sequence, a list of integers which represent the position. You don't specify the rope, you just specify the rope index. And the mask is a 4D array that represents, I think the dimensions are batch size, head size, although you usually just use one and let it broadcast to all the heads, query size, and then the key size. I have a few routines in this notebook that help set that up. So let's see, going through, I'm not sure what we really want to look through detailed, but for the most part, we're coming in, setting up. Allows some default things like positioning. It'll default to just a triangle. Branch locations allows you in like the beam search we were talking about initially, those little branches would all start at the end of the input context. But now we have the flexibility to start our branches at different points within the context. And we can the positions essentially inherit the position of the point that you branch from. The first part in through here, we're just going through and doing the preload of the attention. This isn't chunked or anything like that. It just does it all in one forward pass. So that there is that constraint. And then it generates the caching of the key values. And then through here, we're iterating through gen length. That many new tokens will be generated. Excuse me. That many cycles through generating new tokens, and then the number of tokens generated each time is somewhere in here. Should be the branch number of branches. There's branch locations. Actually, is it not called out? It's just inherent in the size of these. I thought I called that out. Oh, here it is, number of branches. So it'll generate that many tokens in parallel at each time, and it'll generate it this many times in a row. Anyhow, so preload. At the top of the loop here, we use our logits and generate a probability. It implements a greedy token, so just argmax on the tokens, or you can do a sampling based on the probability. Add those to the output string, and then the mask. So the mask we'll see later, but you start out with one particular full block for the context load, and then from then on, your mask is the query is much shorter because you're only adding n branches at a time, but it grows based on the sequence length for the key index. So each time we essentially add on another diagonal matrix for the next set of tokens that have been added. This is the standard. This is where the magic happens. This is the standard Hugging Face forward call, and you always, everybody be used to seeing the input IDs and the passkey values. The parts that we're using are the position IDs and the attention mask. Those are the two new arguments that we're using. This isn't necessary. I just collect it so we can see what were the positions as they were recorded, kind of a diagnostics, and returns a dictionary of two things. One, output IDs is all of the tokens in kind of the jumbled order that Ted showed in his slide deck. But we also go through and reorder them so that we can get the independent branches, the IDs for each independent branch in order. This is just some utilities helpful for printing and stuff like that.
Yeah, so for those people who are interested, we can go through the code more slowly next week, but it'd be nice just to see some examples of the code actual output. Yeah.
Yep. So just initialize the model, and then here's the simple one. So this is the beam search. Beam search was kind of the first place where, for me, Ted, you said it was more writing than margins. Beam search is kind of where I kind of thought, man, that seems like there's an efficient way to do a beam search. So this is where the first implementation. So we're going to do once upon a time is the sequence that we want to continue. And we will do 5 branches from that. Since we're not playing any games about masking within the context itself, and since all of the branches are taking off right from the end of the input sequence, we just create a diagonal mask for attention mask. This little routine creates the diagonal mask and adds on a couple batch and head dimensions for you as well. You can see here I've represented the attention mask. So stars represent things we're paying attention to, dots are things we're ignoring. By the way, in the attention mask, that's represented as 0 is paying attention to, and minus infinity is ignoring. So it's I think it's already they're taking the log of the probability, I think. So they add it to it, which is the same as multiplying before log. So so that's the mask that we created. The results in raw form, we can see that here's your jumbled mess. This is what Ted showed with his oops. Oh, come on, don't do something. Okay. In his slide, he showed the jumbled mess. Here's after we've separated out the individual branches, and I also added the prompt back in as well. So you can see that in this case, we did not do greedy parsing, we did sampling. And so we got a variety of outputs selected on each branch. The position tensors, so in this long sequence, right, which is represented by the input sequence plus all of this, we're looking at the rope, the index associated with the rope embedding. So in the beginning, you have rope indexes that are increasing by 1, right? So each token rope, you advance by 1, and the rope, it does its little rotating thing. But after, so that's the prompt, the beginning. But after that, you can see that the rope number is not changing. That's because even though these are, four consecutive commas, they are all basically located after the prompt here. So 1, 2, 3, 4, and then must be a space in there after that one. So their location is the fifth location, rope location, after time, right? And then there's 5 of them because we're generating 5 branches simultaneously. So all 5 of those would have been generated in one forward pass, and then probably 2. All of these guys are generated in the next forward pass. And they will all be ID 6. So you can see that rope location, it's copied 5 times. This is the attention mask that you started with when there was only 5 tokens in the sequence. But as we grew, remember there was that part I showed where we were adding this diagonal diagonal matrix at the end of the mask each time. That accumulates, that shows up as a diagonal right here along this line. That diagonal is added once for the first set of 5 tokens, once for the next set of 5 tokens, etc. And so this is the pattern, the attention pattern. That's what that matrix looks like. So one for all the queries, and all the keys are the length of it.
Roger?
Unfortunately, yeah.
What is the difference? I'm sorry, maybe I missed it, but what's the difference between a star and a dot in this diagram?
So unfortunately, I didn't notice that we were using different axes. My axes on this presentation are the query is along the left axis, the y-axis, and the key is along the x-axis.
Well, so not exactly, but so basically, star just means we're letting it look, and dot means we're not. And so you can see on the right here, it's every 5th because there's 5 interleaved parallel traces, and so that's why you always see 1 star and 4 dots, 1 star, 4 dots, 1 star, 4 dots. Is because remember when I said the red tokens can only look at the red ones. So the stars here are the ones it's allowed to look at, and it's only allowed to look at every 5th one.
I see. Okay.
So you don't have to really understand, but you can see how basically, right, the different sentences in the different rows are looking at different spots, and they never have a star in the same place, except for those very, very early ones, the first 5, where it says once upon a time.
Does that make sense, Jerry?
Yeah, it does.
Okay.
All right. We're at time, but Roger, maybe just skip to the output of another example.
Do you want to like something like this then, or
just the next one? Just the next one.
Yeah. So the other
the
other examples we did is multi-question. We look through here. This is the attention mask that we get going into that thing, and similarly that we're generating 2 answers here. And then we did something here where we did writing in the margins we simulated. So in this case, you have an attention mask that says, well, we'll ask, let's see, I think we asked the same question twice. What color is the bike? So that the context is the house is red. That's the first chunk of context. The second chunk of context is the grass is green, the bike was blue. You try to ask the writing in the margins prompt the question. On the first chunk, what color is the bike? After all you've seen is the house is red, and then you ask it again after you've seen the grass is green, the bike was blue, and you can see kind of that's what this is showing. Here's where you're asking the second question, the first question, and you can see the first context, but you can't see the rest of the original context. And by the time you ask the second question, now you see the full context, both of it. And the result is kind of what you might like. The house is red. What color is the bike? And it says the house is red.
Right. It doesn't know. There's no
it doesn't know
mention
about
of
the bike. Right? Yeah.
Right. So in that paper, they then run a classifier over it, and it would say the house is red, and the classifier would say false. There's no useful information here. But the second answer, the bike was blue.
Now it's seen all this, and it says what color is the bike?
Oh, the answer is blue.
the answer is low. Yeah.
And then that is very relevant to the question, and so it would collect the relevant margin notes. And so the point here is that in that paper, they did each one of these chunks sequentially. So they asked, what color is the bike to chunk one? What color is the bike to chunk two? What colors? And they did this for like, potentially, hundreds, thousands of chunks. And we're showing that you can actually do many of these chunks all simultaneously.
So, yeah, that's enough of a flash of that. I guess that the one part, just as a teaser. So, Ted, you like this one the best in terms of describing the performance.
So this is a very short context. So there's no rag here, okay? And then we just start generating multiple completions, okay? And so the color of the line represents how many parallel generations. And so as you go from blue to purple, the number of
Actually,
generations.
Ted, the color of the line is how many characters you've generated. That horizontally is how many.
Oh,
sorry.
Yeah. Horizontally is how many beams. Yeah. And so what you see at the bottom for the blue line is that the amount of time to generate 2 tokens is roughly constant regardless of what your beam width is, the number of parallel, until you get to some crazy numbers like 70, it starts to be a little bit higher. And then, up at 128, it seems to have gone from like 0.05 to 0.06. So
but that's 128 questions answered in parallel.
To get 128 tokens answers in parallel, it costs you 20% more to get 128 times as much data. But that's only 2 tokens. That's only 2 tokens. So if you do 4 tokens, if you start having long answers, not 1-word answers, but 4-word answers, and then green is 6-word answers, 8 is 8, red is 8, and then purple is 10-word answers. Now what's happening is 10 tokens times 128 parallel completions is 1,280 tokens. And now you're starting to see the I/O cost associated, and maybe to a lesser extent the attention sequence length cost associated with that. Remember, this was with a 0 length context. So we started with something that was super short. And so basically, all of the cost of the attention here is in the completion. If you had started with a RAG situation where you start with 30,000 tokens, then just adding another 1,000 tokens would not really. But this is just showing you how, roughly speaking, the cost for doing parallel decoding is almost free. It's not quite. It's almost free. So ultimately, the trade-off is you are trading sequence length for inference steps. And sequence length, at some point when you go high enough, it will start to bite you. But in smaller sizes, essentially what we're saying is multi-decoding is free. You can do 4 parallel decodes at virtually no cost whatsoever, which is just crazy.
Contrasted with a naive approach where you basically have to run the query multiple times. And you can see that one grows hugely, right? From close to 0. It's going to be down one of these numbers.
Well, it's almost it's linear too, right?
It is linear. It is.
Yeah.
It is.
Yeah. The only reason why
linear on the sequence length or
the reason why these don't look worse is just because there's constant overhead for making a function call and calling Hugging Face and all this stuff. So that's actually preventing it from looking worse. Otherwise, it would look even worse. Yeah. So
anyhow, so go ahead.
Yep. No, go ahead.
Somebody had a question.
I don't know.
Nope.
Yeah, I had a remark actually, more so, or a request, I guess. Roger, if you put this on GitHub, I might, or my vote would be you should make it GPL, at least until I don't know, a time in which that is different. Just because think it would be I don't know, it would kind of suck to like get it like immediately forked over to some proprietary thing and then iterated on and yeah. I don't know, just a thought.
Yeah. Objective is to make it available to people, so we'll get it out there.
Right. Eventually MIT, but I don't know, my uh I guess like open source allegiance is encouraging me to encourage that, I guess. I don't know.
Yeah. So my only request would be if you see the potential for this, you know, post where you post, X, LinkedIn, you know, Discord, wherever, because you know, Roger and I talked about, we're not we actually talked about, like, we're not forming a startup. We want people who think that this is valuable to use it. And so yeah, in the chat. I mean, well, MIT would be permissive, right? So the question is, do we want, you know, the OpenAI proprietary multi-decode, or do we want it to stay sort of, you know, in the open domain?
Yeah, my thought being, I would, if OpenAI wants to iterate on it, then I would like them to do it in public as well. And then at some point there will probably be a time when it's like, okay, you can transition the GPL over to MIT if that's how licenses work. I'm not sure, but
yeah, like VLM's going to have their own implementation of it,
right,
right? You know, but yes, this will not help you with training. In training, they're already reading every prediction, right? But for inference, as far as I can tell, it's been a mental block that we've just been assuming we only can read the last one, and we've been treating everything as a sequence, not as a tree or a forest. But there's nothing in the attention calculation that prevents us. And there's even a few exceptions where it's not literally a regular tree. Like Roger and I have an experiment we want to do where we actually skip rope numbers, where we just say your data went 0 to 1,000, and then we didn't start at 1,001. We just started at 2,000. What happens? And we think that if it's a small number, like 1, 2, or 3 skipped numbers, then the model's going to be very confused what the missing words were. If it's a large number, we think it's going to just basically ignore the gap.
Um,
And it might infer
Sorry,
like they're in context learning. So like you know, you can take a model and be like, compress this for another model, and it'll come out like gobbledygook, and they won't. But then you paste it into another model, and they'll make total sense of it. So in theory, like you might be able to get away with like doing the same thing to your positional embedding.
Yeah.
Cool.
Very cool.
Sorry, can
Extremely
I ask a
cool.
question?
Yeah.
So in case of like the beam, right? Like your sequence length is growing, and attention we all know is like O of n squared, right? So your sequence length is growing by the factor of, like, in an exponential, right? Like the log tree expanding. So isn't the attention calculation gonna take over like after a few, like if you go like up right now, like you're showing like the sequence length up 10, right? You're adding 10 more tokens. So if you do it like 20 or 30, like the sequence length is gonna explode and the attention's O of n squared is gonna take over.
Yes, that's right. So this is intended for fairly short completions.
Mm-hmm.
And the trade-offs are the best when you have long context and short questions and short completions. And that is actually the majority use case, right? So you have a big chunk of code and you ask a relatively short question about it, like, why am I getting this error? How can I optimize this one function? And then it outputs you one function rewritten. It's not rewriting your whole repo, right? But it's not every use case. And so if you really did want it to generate a 50,000 token long chapter on linear algebra, you shouldn't have it also simultaneously in parallel output all 10 other chapters of your book, because that's just going to bloat your sequence length like crazy.
Well, and then you can repurpose your tokens a little bit too, right? Like you could use reasoning tokens for sequence length, or tool calls, or kind of whatever you need to, whatever sort of extra stuff you need in addition to just answering the query too, I feel like would be the thought.
Also, like there's gonna there's gonna be some bloat in there as well, right? So like if one of the tokens, like one of the questions answer just ended, and like the other question is still going, right? So you'd be appending the end of sequence token to all the tokens, and that shouldn't be in the sequence length anymore. But there might be some ways to optimize.
The thing is that the trick is that you are generating multiple tokens on each pass. And the thing is that, and the way we've captured it right now is like n branches, right? And you would run into that issue. But with a little bit more management of this bookkeeping, there's no reason that you can't, once one of those 5 questions is done, start the sixth question and the remaining slot. It can be completely dynamic. And I think there's the cache management, it can get I can see with these live ones like the beam search, Ted, you and I talked about on the beam search, that you're going to end up with these dead branches that you abandon. And right now they occupy space and they're bloating the sequence without adding any value. But Hugging Face does have an interface for managing the cache. And so again, some bookkeeping, you could kind of, when you get to a certain point, select out the stuff that you want, garbage collect, and do one pre-fill pass for the stuff you keep, and then continue on again. It's just all bookkeeping.
It's operating systems tough, garbage.
One form of search that Roger and I have talked about is, let's say you're doing something that's very reasoning heavy, okay? And you do not a full beam search, but just a multi-completion for the next sentence, okay? And we recognize some sentences might be longer and shorter than others, so they're not all going to be perfectly in unison. But right now, generally speaking, you're doing greedy decoding with 0 temperature when you're doing reasoning, right? And if you choose one bad token, you can kind of paint yourself into a corner. But so what if you then just said, I'm going to do 10 parallel multi-decodes of the next sentence until I get to the period, whatever, on each of those 10 sentences at roughly the same time, not exactly the same time, right? And then you do some calculation like an entropy calculation, Warren, or like an average, some kind of geometric average, logit or something like that, to pick the best of the 10 sentences. Now you don't have this, I did one token and painted myself in a corner. I waited to see which of the sentences was the strongest. And at that point, I accept the entire sentence from those 10 and then continue generation. The cost of that with multi-decode is only the ratio between the average length of the sentence picked and the max sentence length, because you're always going to have to generate up to the longest of the 10 sentences. So if on average the longest sentence is 15% longer than the sentence you pick, you're going to have a 15% more inference steps because you waited until that longest sentence. But again, assuming that each inference step is roughly identical cost, you're going to have like a 15-20% decoding hit for getting to choose from the 10 best next sentences. This seems like a really killer way that might boost chain of thought.
Makes sense.
Yeah, I think all those ones where we're carrying along multiple threads simultaneously and pruning off, they're not long threads, they're kind of exploring different areas, and we're pruning them off, garbage collect as we go. I love those. The idea that for free I could be, the language model could be anticipating my next question, 10 next questions, that type of thing, or where you're exploring it. What was the one Warren brought where you're exploring and evaluating the branches based on entropy, I think. Those type of implementations sound cool.
Kind of like you have like 10 ideas in head and then you choose to pursue one.
Yeah.
Well, exactly. Yeah. The graph reasoning here seems really cool to me too, where it like, if you can, there's like something here where I like want to bounce in all the different directions while we're figuring out which one is the optimal one.
Especially if it's free to explore all of them simultaneously.
Okay.
One interesting things with graphs is a lot of graphs, Warren, are high cardinality but short path lengths.
Mhm.
And here with multi-decode, cardinality is relatively free, but path length is where you pay for inference steps. So you could hypothetically say, I did a 50-way branch at one node and a 3-way branch at the next node, and you're maintaining quite a few parallel paths, but as long as you only do it for 5 hops, your sequence length isn't really bloating that much. And so you could afford some relatively high cardinality searches of this graph in parallel at almost no inference cost. It's like crazy. Well,
Yeah.
actually, if you do 5 hops, you're paying 5 inferences for potentially choosing one next token, right? So that 5 times penalty still applies. But the fact that you actually searched hundreds of nodes of the graph with only a 5 inference penalty is crazy.
Yeah, right. Especially if, you know, like if it's a knowledge graph and you have like, you know, relatively high signal information per, you know, step that you're going to make. That could be really, you know, that'd be a hell of
Yeah,
a lot more effective than the human subconscious. I'll give it that. So,
yeah. And again, this isn't even some like, oh, let's build a new LLM. This will work with every existing LLM as long as you just have, mask and rope support. No special training, no special hardware. Obviously, it'll run a little faster if you have a really good implementation of the bookkeeping, right? Um, but it doesn't really it's not like, hey, we invented a new LLM model, right? That has these special heads with special loss. It's like, no, use this with any existing LLM.
mm-hmm. Yes, very much so.
All right, are we through for tonight?
I think so.
Okay,
Yeah, I think so.
So we're through.
I'm gonna kill the recording.